Okay, good morning. Today, as I said, lecture will be from 8:30, 9:20, then 10:30 to 11:20. I'd like to complete the example on eccentric unsymmetrical bending. We have finished it already, but a student asked me a good question. It's like, now you taught us a way of finding the neutral axis. If I want to use the formula, okay, how to apply the formula, okay. Then after that, we're going to start a new topic. Okay, it's one of the most difficult to understand topic in structure analysis, which is shearing stress. Okay, so let's look at the example of unsymmetrical bending. I show you guys a technique on Wednesday. Okay, so a particular student to ask me this question, Eugene. Now, what if I want to use the formula stress x is equal to px over a plus by my over Iyy multiplied by z minus by mz over Izz multiplied by y. And how does it work? Okay, and we realize that we only have one equation. Okay, we want to find y and z on the neutral axis. How about do we do it? Okay, so at the neutral axis, anyone have any question, just type down and ask me on the spot if you don't know where I'm getting on with this. So at the neutral axis, we are aware that stress x is equal to 0. All right, so the above expression will be equal to 0 is equal to px over a plus by my over Iyy multiplied by z minus by mz over Izz multiplied by y. Right? So we want to find the first thing that I'm going to pick. We want to find the intersecting point of the neutral axis along point A and point B. Right? Along point A and point B. And along point A to point B, we know y is equal to positive 1.8 divided by 2, which is equal to positive 0.9. Why? Because at the center it's 0 down here. If we look at along the line AB, right? And this is 1.8, not 1.9. I do apologize. So this distance is 1.8. Okay, half of 1.8 is 0.9. So along AB, we know that y is fixed at 0.9. Okay, so we're going to apply the above equation to find z. Okay, so what we're going to do? We're going to find z. Okay, so this is equal to 0. Px is equal to 900 divided by cross-sectional area of 7.2. Then you have plus my is equal to 800 divided by Iyy, which is 9.6, multiplied by z minus by mz, which is 540. Now, all this we know is positive here. Why they are positive? Because we know that the moment about mz in this direction. We know that the moment about my is that direction. So using the right hand rule, the moments are all positive. Okay. Then divide by 1.944 multiplied by positive 0.9. Okay. So this will be equal to 800 divided by 7.2. 900 divided by 7.2. So to 0.125 plus by 800 divided by 9.6, which is equal to 25 over 3 minus by 540 times 0.9 divided by 1.944, which is equal to 250. Okay. So 125 minus 250 So it's 125. So 250. Wait, 125. So this is equal to 0. It's equal to 250 over 3 z. So this will be equal to minus 125. So now we need to find z is equal to 125 times 125 times 3 by 250. Okay, so 125 times 3, 250 is equal to 1.5. Positive. Okay, means positive, right? Positive 1.5 means is at the position from here to here. This distance is equal to positive 1.5, right? Because z going positive is going towards the left. When we found our answer from A, our distance from here to here is 0.5. So we got the exact same point. Okay, so let's do another time. We look at between B and D. Okay, so we want to find, I will just find neutral axis between point B and point D. Okay, I will copy the image down, so I won't move the page so much. You get a headache, I get confused. Okay, so same thing. Okay, so apply the formula. So 0. Now what is different now is now z is equal to minus 2, right? Because BD is over here, so BD, the z is equal to, we know that at this point z is equal to minus 2, right? Okay, so you have px over a, so 0, px over a is always the same, 125, right? Plus by 800 divided by 9.6. Then this one multiplied by minus 2, and then minus by m. Mz, what do you mean using right m? 540 divided by izz 1.944 multiplied by y. Okay, so this one you will get 125 plus 800 times by minus 2 divided by 9.6 is equal to minus 500 over 3 minus by 540 by 1.944 is equal to 2500 over 9 y. Okay, so I'm going to continue over here. So 125 minus 500 over 3 is equal to minus 125 over 3 minus by 2500 over 9 y is equal to 0. So therefore y will be equal to minus 125 over 3 multiplied by 9 divided by 2500. Okay, so 125 times 3, 125 times 9 divided by 3 divided by 2500 is equal to minus 0.15. Okay, let me do it again. Minus 125 divided by 3 times 9 divided by 2500 minus 0.15. Okay, so from here 0.9 coming down is 0.15 because minus, right? And our answer is what? Our answer from is 0.75 from D. So this distance from this distance is in fact 0.75. Okay, and because this entire distance is 0.9. Okay, so this is how you apply the formula if you have to, okay, to locate the position of the neutral axis. The only thing you have to be careful is you need to know whether your moments are positive or negative, okay, and everything is relative from the centroid. Okay, because means centroid means what? 0 is at the center. Y positive is upwards. Z positive is towards the left. You have to be careful with that, or not you'll be in a bit of trouble. Okay, so either way is fine. If you use either way for the
Eugene,
yeah, yes,
why is the Z -2?
because Z positive is going towards the left.
So we don't use the 1.5 that we calculated?
Right. You're talking about the second example, right? Where Z equal to
Yeah,
-2, right?
but
Because
in the previous part we calculated Z to be the 1.5, no?
yeah, previous one is the intersection of the highlighted yellow. This one we are calculating the intersection of Eugene, I go. We are calculating the Y intersection along BD. Hello? It's different.
Yeah. Okay.
Okay. So that's why the first one we want to find Z. The second one we want to find Y.
Okay. Thanks.
Okay. So the positions are the same. Okay. From the technique I show you on Wednesday. Okay. It's exactly the same. Right. You decide which one to use. For me, I rather use a simpler technique. Okay. It's just equation of a straight line. They are all on the same gradient. Okay. Right. Any questions so far? Okay. I don't hear anything. I don't see anyone typing anything. Okay. Now, the next topic is going to be about shearing stress. Okay. And this topic, I think when you guys were taking 2P last term, probably Dr. Koshi did a very quick. Am I right? Were you all tested on 2P regarding shearing stress? Anyone? Or is just an introduction? Anyone? Could you remember? Y'all do any question on it? Anyone?
I think we weren't able to get to shearing stress.
Yeah. Just a bit. What were your exam in your final exam? Yes or no? Did you all do any question like in the exam? Like actually, no testing, right? Okay. Thank you, Wally. So shearing stress is one of the toughest topic for a mechanical engineer to grasp the concept. Okay, it's really, really tough. I had problems with it. Okay, when I was undergrad, when I was learning this topic as an undergrad, even my prof touched on a very surface aspect of it. So when I'm teaching this course, I went into depth. Okay, as I said, this is my 7th time teaching it, and the complexity is this. Okay, we as engineers, we like to see things visually. Okay, shearing stress is one of those components that you cannot just see things visually. You have to apply rules and laws. Okay, how many of you like electricity as a course or electronics? You all love it or hate it? Anyone, please? Love it. Only one love it only. What happened to the rest? And a few love it. Okay, so a few of you enjoyed, which is good. Okay, I did not enjoy my electricity course. I'll tell you why. Okay, I hate to obey the rules. Okay, what do I mean by the rules? Like for example, can you see current? Can you see voltage? Can you see resistance? The answer is no. But if I relate something similar to electricity as to a mechanical engineer, can you feel flow rate? You say, yeah, flow rate is how much water is coming through. Can you sense pressure? Yeah. If the higher the pressure means the heavier I'm carrying or the load, right? And can you see what will happen if the diameter of the pipe get bigger? Yeah, the water is easy to flow. You can visualize this. So in electricity, it's the same in a certain context. The bigger diameter pipe, right, means lower resistance. So resistor is lower, right? The flow of the fluid, okay, is your current. And the pressure is your voltage, because when you measure pressure, you measure from 2 points, right? You don't measure pressure from 1 point. You have to take from atmosphere and measure on another point, or along the pipes you measure at 2 points. So the same for electricity. If you measure voltage, you measure for 2 points, right? Now, shearing stress is very similar in that context. You have to apply the rules. Like for example, in electricity, right? When the resistors in series, what rules do you apply? Can you